So, but when you're traveling up north, you'll find you mentioned some oil burners, whatnot up there. But down here in the surrounding states, you'll find primarily the types of systems that we'll find when we're dealing with either a package or a split system. So let's look into this, and we'll see what we can do to make ourselves more accurate and a lot faster in our troubleshoots. Because now we know what each system is going to have in common. So students, when we're looking at the types of systems that we discussed in lecture this week, we learned that there are two types of systems that we can anticipate in residential under 5 tons. We can anticipate our package system or our split system. When we are talking package or split system, we are defining where are the components of the refrigerant cycle. Do we have two components? Do we have the condenser and the compressor outside in the condensing unit, the high pressure portion, and do we have the low pressure portion in an indoor machine of some type that's inside of the home? When we have a package unit, all the portions of the high pressure, low pressure of the refrigerant cycle are all contained in one machine that usually sits outside of the home. You usually see those when there are size restrictions. But if we're not talking about a package unit, what we're going to find is a split system. When we look at the majority of the systems that we're going to work at, and also the majority of systems in new construction, these are split systems. If I had to give a number percentage in 25 years and thousands of machines worked on, I would say about 97% split systems, 7%, or excuse me, 97%, about 3% package units. Unless you are catering to exclusive, 55 and up communities, then you won't see too much. But you have plenty of clients that are there, so you will see split systems. But the primary will be split systems. You'll see package, but you will see split systems everywhere. And then when we're talking a split system, we are splitting it into two portions: our condenser, our high pressure portion, and then our indoor machine. The reason we call it an indoor machine is we haven't defined what type of indoor machine is, what type of indoor machine this split system portion is. Because when we're talking about the indoor machine, we have two options. We're either going to be a combustion furnace or we're going to be an electric furnace. The way the indoor machine produces and provides heat for the home gives it its designation of the type of indoor machine it is. So in our split system, our high pressure portion, which is separated, in our split system where our low pressure portion is separated from our high pressure portion, your indoor machine will either be a combustion furnace or an electric furnace. In our split system, lecture teaches us that once we split the system, we have an indoor machine. We go to the condenser, the high pressure portion, and we'll find we have one split there. We are either going to install a heat pump condenser or a straight cool condenser. So these are the 4 machines that we can anticipate you work on in residential under 5 tons. It comes down to 2 types of condensers, 2 types of indoor machines: an electric furnace, a combustion furnace, a straight cool, and a heat pump. But what do all these types of systems have in common that will help us troubleshoot accurately, help us be accurate and quicker with our troubleshoots? We have to think of what they share, of what they all have in common. Lecture teaches us that we have a line set, and our line set is between the high pressure portion and low pressure portion of every split system, regardless of the type of condenser, regardless of the type of indoor machine. You will have a line set. And if you don't have a line set, then you do not have a split system. So we can count, now we can anticipate. We will have a line set regardless of the type of split system, regardless of the type of indoor machine or condenser. We learned that our line set, is composed of 2 refrigerant lines and 1 low voltage control. We have the suction line. That is the first one. Our low pressure suction line is part of the line set. Lecture teaches us that the typical sizes that we will find in air conditioning in residential under 5 tons is going to be either a 3/4 line set, suction line, or a 7/8 suction line. So now we know that every split system will have a line set, and the line set in the suction line of the line set will either be 3/4 or 7/8. We learned in lecture to be on the lookout for the 5/8 suction line, much smaller than a 3/4. This was okay in maybe 89, 91, but the machines that have been being developed for a very long time and engineered are not made to have a 5/8 suction line. In residential under 5 tons, we will have either a 3/4 or 7/8. When we're talking about the other refrigerant line, we're going to talk about the liquid line. Our liquid line also leaves the, again, indoor machine, travels along with the suction line to the condensing unit. The reason our suction line is covered in black, as we learned in lecture, this is Armaflex. This is rubberized Armaflex to cover the cold suction line, because if the suction line is not protected from a hot environment such as an attic, it will sweat and condense profusely, and homeowners will not be happy. Will damage property. Outside, when we don't see black Armaflex covering our suction line, yes, condensation won't be an issue, but the actual exposed suction line will be gaining. It'll be gaining heat as it's traveled because it's not insulated. So when we see this, we see a physical representation of the Armaflex covering the suction line. Covering the suction line that brings refrigerant back from the refrigerant cycle. And on top of the suction line Armaflex, that's where we will find the liquid line. We will find the liquid line every time because it's a split system, and every split system mandates this line type. With our suction line, our liquid line, we learned that we are looking for a certain size. We learned that 3/8 is the size for our liquid line. We learned in lecture that 3/8 is the liquid line that is used when we have a line set between a split system. Again, gentlemen, regardless, it's a split system, regardless of heat pump, regardless of spray food, regardless of combustion, regardless of electric, your liquid line set will be 3/8. And we learned, just like the suction line, we need to be on the lookout, because you will find 1/4 inch suction line. Gentlemen, that is the diameter of a pencil. You cannot mistake it. It is too small. It'll work, but air conditioning is very forgiving. You know the saying, I taught it. That is what we need. It will work, but it will lose performance and efficiency. Can we expect to get 10 years out of a compressor running on a 1/4 inch? No. So being able to anticipate now that every suction line between, regardless of a split system, will be a 3/8. Every machine under 5 tons brand new carries a 3/8 liquid line port on any machine, all of them. What else, students, is inside our line set besides the 2 refrigerant tubes? We built them, David, in lab.
I forget the name of the cable.
We're looking at it on the wall, my man.
I know.
What's on the wall? It's a certain wire.
Yeah, I know, I just don't know the name of the wire.
Well, look at the wall. What's on the wall, my friend? The thermostat wire. Very good, Comey. Very good. Thermostat wire, 24-volt thermostat wire. Every line set in our split system, regardless of combustion, electric, heat pump, or straight cool, will have the line set, and the line set will include thermostatic control, a 24-volt wire that is traveled in what we can call a bundle, because it encases 5 to 7 other smaller thermostat wires. We understand now that the split system, regardless of its machine, will have its line set, and you will have a thermostatic control 24-volt low voltage wire, because this is how we can manipulate and control the compressor contactor. So now we see a thermostat wire between one. And why is this important? Why is this huge? Because I told you, in your troubleshoots, you may not know, is this electric furnace, combustion, heat pump, straight cool? You may be so lost in the troubleshoot and not know which way to go. But when you understand that you're on a split system, regardless of the type, go outside of the air handler, right next to it, go outside of the condenser, if that's what's joshing you, and grab that line set, and grab that low voltage wire, because once you have it, you dictate control. You dictate where it goes, along with the rest of the system. You can always count on the line set, because this is where you will find it. It doesn't matter what's on the ends of the machine. It matters where you connect the wires from this low voltage thermostat wire. Remember, there are 7 control wires. 7 wires we can send voltage on independently. So let's look at this. We did, in our discussion, we had service calls. And I remember everybody, when they did their service call, had a very, very wide troubleshoot. Why? We have a problem, furnace turned on, I messed with the panel, and then it turned back off. And then everybody wanted to inspect the breaker box. Well, certainly, we just did lecture on breaker box. That's great. That's why I would start 2 to confirm. And this is before we did our troubleshooting path. So if we get this call, now we understand. What is the question we ask once we declare who we are, what we're doing there, and ask them how their AC is? What is the next question that we will ask the client, the customer? After we introduce ourselves, to define our troubleshoot.
You can have air blowing,
Yes, or
if it's just.
no air at all. Brilliant. That's it. We walk in and we see, that's our first question. We walk in, hi, John with AC Medic, here to take a look. What's going on? They tell you. And then the next question is, so let me ask you, we get hot air at the vents or no air at all? The answer to that question defines your troubleshoot. Now we learn, do we go outside? Do we start at the machine? Because if he says yes, there is air, but it's hot air. Yes, now we go to the condenser. That's correct, because now we look at the system through the eyes of our meter. If this machine is spinning, if that fan motor is on, L1 and L2 are present. If that fan relay is engaged and that indoor fan motor is spinning, our transformer is receiving primary and is producing secondary, or that fan relay wouldn't close and that fan wouldn't be spinning. And that pushes us to the condensing unit. Instead of going directly to the breaker box, we go to the condenser and we isolate from there. But when we ask the question, they say, yeah, there's no air, buddy, not moving at all. Then where do we go? Where would you go? Indoor machine? Correct. We wouldn't want to start with the breaker box unless the customer says that direct, snapping the breaker, it snapped the breaker, it gives you a history of a snapping breaker. We wouldn't start there. If the answer to the question is nope, no air at all, we're heading straight for the indoor machine. Yes, there's air, but it's hot air. Now we're off to the condensing unit. Because once there is air blowing, although it's hot, we cleared all of the high and low voltage components, because we know now with our meter where we could get a reading and take a picture of voltage arriving Take a picture of 24 volts leaving the secondary side. So we know that in our mind's eye, that's why we step outside. Now, if we are told that nowhere is running, now we come in here. And we don't go to the breaker box because once I remove my panel, I can check to see if I have both legs arriving. And if I do not, then off to the breaker box we go. In fact, if I do not have voltage, I would take and I would back up and disengage L1 and L2 and bring it away from the connections. And then I would test voltage again. Once I confirm there's no voltage, then off we go. Go ahead, please.
Test the amperage when you take L2 and L1 off to see if.
One more time with me.
When you take L1 and L2 off, you check the amperage with your meter to see if everything is.
Well, with the amperage, we were measuring the load draw, work being performed.
Correct.
So, my friend, very good. Voltage is in the right interval, but yes, we would check voltage arriving, our first meter setting. Confirm. And once, if we take this off and we find there is voltage, both legs, then our troubleshoot goes inward. That's only after we confirm that 240 is present at the indoor machine. Now, what we must do is look at what we understand. Now that we understand that regardless of the type of condenser, regardless of the type of indoor machine, there are certain similarities. The line set that connects them. And what else? This is an indoor machine. This is a split system. I know because I'm in their attic. I'm not outside at a package unit. So we're in here, and students tell me, what do you see when you look at this? Give me the physical description of the exterior walls of the machine and what penetrates the machine.
The thermostat lines, the bundle,
Thermostat bundles, thermostat control, these are excellent, excellent, excellent designations. Yes, sir. And how many of those do you see entering this machine? This would be 2, correct. But then look over here. We have to have the other type. So if we have secondary 24 volts, what do we need over here? Coming in, L1 and L2. So we have high voltage and low voltage. So for every split machine, regardless of condenser, regardless of heat pump, regardless of straight cool, regardless of combustion, regardless of electrical, every exterior will have high voltage entering and 2 thermostatic control bundles or thermostat wires. Some folks say thermostat wire, but to me that implies 1. This is a bundle of multiple thermostat wires. That's why I like thermostat bundle. We have 2 thermostat bundles. Not 3, not 7, not 8, not 1, 2. Every time for every split system, regardless of what type of indoor machine or condenser. Where do we see our thermostat bundles ending when they leave the machine? Where do they terminate? At the thermostat is 1. Very good. And our other? Beautiful. The condensing unit. Excellent. One of our thermostat wires exits and we have it behind the thermostat. And we also have one at the condensing unit. And where do both of these wires originate from? They don't originate from here. Where do they originate and where are they landing? The indoor machine.
Indoor machine, and then they end at the thermostat.
Brilliant. Kobe says the thermostatic control, the T-stat wires, the bundles, they originate from the indoor machine and they terminate at the thermostat, at the condensing unit. Every split system will have a thermostat. Every split system will have a condensing unit. Knowing to anticipate where to find the 2 thermostatic control wires that originate where in the indoor machine is what gives you the understanding that regardless of combustion furnace, electric furnace, heat pump, straight cool, you can count on looking for your control, but where do you find it? You open that panel, you see those wires and you say, no way. I say, put the panel back on and isolate the wire before it even enters the machine. I told you, once you have the thermostat wire as it enters and you grab it from the indoor, it is yours. You have it now. Now you connect it and you control it. With the thermostat wire inside of here, I dictate what is connected and I dictate what happens on the other side for both the thermostat and the condenser. And that is for every split system. Students, respect thermostatic control on the split systems. 2 thermostat wires, 1 high voltage, every machine, every application, because this is what allows you to understand how we translate the theory. This is theory, students. And I've seen all of you when we've done this. But you look at this and you think this doesn't look like an air conditioner. Not even a little bit. And it doesn't. But it's accurate and it represents the laws and rules that apply when we're talking high voltage, low voltage systems. We need to keep in mind that when we're talking high voltage, low voltage, the reason it's so crucial is because high voltage, low voltage is what shakes so many air conditioning technicians. It shakes them right down because they're trying to figure out the physical when they don't have the theory. We're trying to figure out the theory and master it, but we don't have. We do have the physical, but it's so isolated, so separated. And trying to take our theory into our physical now on the board, we do it at the same time. This unit is more or less to scale. This is an indoor machine. Is this a combustion furnace or is this an electric furnace? It's an electric, very good. How do you know on site? L1, L2, L1, L2. What inside of this electric furnace mandates L1, L2? What needs to pull that highest amp draw? The potential amp draw. There's 2 things there's 2 loads in this indoor machine. One potential load is the fan motor. The other potential load is a 10 kW. Absolutely. Absolutely. It's the heat kit. It's the heat kit that we learned in lecture comes in 3 sizes. 5 kW, 7.5 kW, and a 10 kW, our largest. What is our typical amp draw for a 10 kW heat strip? Clue, very similar to our stove on Thanksgiving's Day. 52, typically 52 to maybe 56 amps, 52 to 54. 10 kW pulling typically 54 amps, then that's with every burner going, oven set to 500 and every burner on. That's where you're gonna hit that max, or the most it can draw. So we're pulling this on the 10 kW. What kind of wire would we require to be able to safely carry 54 amps? Enough, say it louder, my man. Louder.
Yeah.
That's it. 6. Very good. Excellent. So we have our 6 wire, simply because we're looking at 10K and we're not letting it tell us. We get to look and confirm. Those are probably the largest wires I've ever seen in my life. That is obviously 6. Yes, it is. It's huge. It's just like almost the pinky. It's immense. But we have a number 6 wire and we're getting voltage. We receive full voltage when we set to VAC. And when we set to VAC, we need to figure out why it's not working. So when we try to figure out why it's not working, where do we go next? Right here, this is a troubleshoot for inside when the indoor fan motor is not working. Because we need to see how we can take this theory and put it into the application that we're in the field. So where do we go? Translate it out, that's excellent. Transformer. Transformer, excellent, 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 excellent. the transformer right here is where Comey would continue his troubleshoot if he was told the inside machine is not working. He would confirm with VAC that he does indeed have both legs of voltage via a reading of 238. He would then go directly for the transformer. You see, Comey didn't want to go for the loads. Comey didn't want to go for the relays. You know why? Because Comey understands the transformer, when we're troubleshooting, whenever we're deeply troubleshooting an air conditioning system, when we've lost control, we have no idea what's going on, realize once you've confirmed voltage, your transformer is the neck, is the jugular. The transformer is the neck. You get to this transformer. Once you have confirmed all voltage at this transformer, you are prepared to remove every wire and rewire it with the principles of the theory and application. And as you rewire it, you understand that when you see these wires, when you get to the components, you dictate what wire goes where. You dictate where the voltage goes. It is up to you. You dominate it. You dominate the voltage. You control the voltage. You control the voltage once you know where it begins, where to find it, and what to do with it. And then you can rip every wire out. So let's do that. Let's do that in application. Let's do it in theory. Let's do it at the same time. So what is the first thing that we want to do for our transformer?
Test secondary.
Comey says he wants to test the secondary side. Very good. Very brilliant, because when we land at L1 and L2, we find our needed voltage. When L1 and L2 are here, they go to a transformer. When they go to a transformer, L1 and L2 proceed uninterrupted to the primary side of the transformer. When they proceed uninterrupted with nothing breaking it, no relays, no possible break, that means that the primary side of this transformer is currently getting its voltage. And when it's getting its voltage, you go directly for the secondary. Because with the secondary, now you understand, if you have primary here at your lugs, you have two direct wires to the transformer, and you means that you have your 240. But if your secondary is not present, you have got a bad transformer. You will never find that without a VAC reading on your meter. Now, we've removed every wire from the system. Let's put it together. You have connected the primary voltage on the transformer, have you not? Excellent. Now, for this portion, I will be standing at this indoor machine. I will be standing at this electric furnace. I will be holding a tray that has every color wire, every size, and I can cut it every length, add connectors, whatever I need to do. And I want you to instruct me on what to connect where to make this theory in real life as we're standing here. Please locate the transformer. In the indoor machine right in front of us. Locate it through. Have you found it? Brilliant. Comey's located the transformer. Do you see the primary side? Okay. We agree that L1 and L2 come in and wait there for the connections. So on this transformer, I need you to designate for me an L1 and an L2. Almost designate an L1 common. Because for a transformer, it doesn't mind where you put its primary. It doesn't even mind where you take the secondary. Just the fact that the voltage is there will make the transformer produce its secondary. So where would you like L1 to be on your transformer? You can say left, top, right, bottom. Which connection? Top left. So you're going to designate this. There's no wire, there's not a wire in here. And you have designated top left of this transformer to be your common L1, correct?
Yep.
Okay, so what I'm gonna do, if it's cool with you, is I'm gonna get a piece of black wire and I'm gonna connect it, where I connect it to this connection here, and then where I connect it here to this one. No, what, no, negative, where, which one, left? Oh, that's the L1, correct, that's the L1, so yes, I'll connect it here, very good, what color? There it is, okay, okay. All right, let's do that. All right, here we go. What's next? Where would you like our L2? L2 is needed on the primary side of the transformer. Where would you like L2, sir? Bottom left. Very good. I'll make the connections. Where should I originate? Where should I start? L2 side on the right to one of these connectors here that's waiting for me, correct? So sit and wishing on wait, okay. And the red one, got it. Ah, very excellent. So we have now primary voltage. Now, Kwame, if you test your secondary, you have 24 volts. You find 24 volts here. Now, how do we replace every wire? Where would we start now? Where would we start in reconnecting every wire in this machine once primary has been delivered? Where did I say the neck is? What is the neck of troubleshooting these systems once you have voltage arriving at the machine? You've already given me the right answer once. The transformer. So you've connected it, correct?
Correct.
Now let's look at what's left on the transformer. Let's get that figured out before anything else. That's correct. Now, we look at this and we see that we have primary voltage that has been connected to the primary side of the transformer, both bottom in theory, and looking up at the top part, you'll see the primary and secondary on the right, and you'll see a red and a black wire bringing L1 and L2 to the primary side of the transformer. Very excellent. Now, what is being produced on the secondary side?
Connection common to the server side.
Very good. Let's do it in theory first, and then we'll move up. That way, it's brilliantly how we can go from what we have on the paper and what we have in our brains. Because we have this memorized, but it doesn't look like an electric furnace yet, but it will now. So let's start with what we know. What colors do we go typically on the wires that come out of the secondary side?
For common, I thought it was just still red.
Well, red is going to be control.
Oh, yeah.
So what would be the other color? Blue, correct, very good. So we'll go ahead and fill one hole blue. Very good. And then we'll fill our other one red. Actually, gentlemen, this is for here. I like to use the pink, just because pink is going to be a little different. So let's grab, I know there's a pink color pencil in there. So grab our pink, and then we're going to fill this one in pink. Excellent. Now you did designate for me, on the primary side, you designated this my L1. So, and that would designate this L2 on the primary side. That is what told you where to connect to L2. So, tell me, what is next? What are you going to designate for me? Our secondary side needs a designation. So designate which one for me you'd like to see be designated. Because we have two options. We have common and control. So which one would you like where?
Control on the bottom.
Control on the bottom, very good. We're going to go with control on the bottom. Our designation has been set. Now, once you set that designation, now you can say what is opposite. Because once you set where you set your initial designates where you set your second. So you set control to the bottom. So what does that by default make the top connection? Common, very, very good. So we have common. We have common here, secondary low voltage common. Now, when we think of transformers, what we have to remember is when we think of transformers as the neck of any split system. Again, the beauty, any split system. I just said for machines by saying split. When we say the transformer is the neck of every split system, it's because being able to rewire both the theory and in real life begins with connecting the four connections on the transformer. Once we have primary and secondary where it's supposed to go, we have removed all the low voltage from our real life application. And then we can move to the high voltage using the same principles that we use for low voltage. And then we will have a completely rewired machine that you rewire. Now, when we think thermostats, you have got to think relays. Relays exist for the thermostat, and the thermostat exists for the relays. You have one relay, typically you have one relay for every load. Notice I said load. I didn't say a particular, I said even that, I'll tell you this, you have one relay for every L1, L2 load. And in this electric furnace, what are our two loads that will potentially produce work? What could produce an amp draw inside of that indoor machine?
Indoor fan motor?
Absolutely, indoor fan, and what else? What produces the most amp draw in that machine? The heat. So, our indoor fan motor is a load that requires both L1 and L2? Absolutely. Our other load is our heating strip, because this is a heat kit. And we said there are two types of indoor machines. And when we have two types of indoor machines, it's the heat kit itself. It's the presence of the heat kit in the indoor machine that designates it as an electric furnace. Because it's either going to be a 240 volt L1, L2 heat kit inside of your indoor machine, or it won't be, or it will be a combustion furnace. And when you see a combustion furnace, you will see a natural gas line coming in, a flue with exiting, venting. So when you know that you're going to have this, you can anticipate this is what you're going to see in this type of system. So now moving on, we have the transformer, and we have relays, and we have loads. In this entire system, how many loads do we have? We've got two in the indoor unit, two in the indoor machine. What do we have? How many loads do we have outside? How many potential loads can turn on and draw and create an amp draw? And are condensing, regardless of heat pump or straight cool? Two. Very good. It would be the compressor itself
And the fan motor?
and the condensing fan motor. In our condenser, that's where we find our compressor contactor relay. We've seen a compressor contactor relay. What we need to recognize is that both the outdoor fan motor and the compressor are controlled by the compressor contactor relay. So I'm going to ask you, what's the total amount of relays in this entire split system? How many relays are in the entire split system?
4.
Well, those are controlled by one. Out there, there's 4 loads, but 2 are controlled by one. So how many total? Total relays between the indoor machine and the condenser? 3. Brilliant. 3. Students understand this is the baseline. This is a straight cool with a 5 kW. You need everything you see on the theory is what you need to be able to cool and heat a space. You need a minimum of 3 relays, 2 in the indoor machine and 1 at the condenser. So when we have our relays, what do the relays, there's 3 relays. We need to connect all 4 connections on the transformer to move forward and have half of the wiring done and then move to high voltage. So our common, our secondary common, what is every relay saying to the transformer? What does every relay say first? Put the common in my hand. Common in the hand, that's right. We learned in lecture that every relay has 2 hands of low voltage and 2 hands of high voltage. And when we have a transformer, a secondary transformer, every single relay, the fan relay, the heat sequencer, the compressor contactor outside will have 2 hands out on low voltage. And they will tell the transformer, put the common in my hand. They want this common. The only purpose of this 24-volt common is to land in one hand of every relay in the entire split system. Once we land common, it's done what it needs to do. It's there, it's done its job in the relays. So let's connect our common. Let's put the common in the hand because that is what every relay says. Put the common in the hand is what the relays say. The relays want their common before any other wire is connected because it's that crucial. So let's do that. Let's put the common in the hand of every relay. On theory first, where would we go? We have 2 relays to connect. Our bottom connections are low voltage. Our top connections are our high voltage. Indoor fan motor, and then what's its relay? That's its fan relay. And then what would be the relay for the 5 kW heat strip? Correct, the heat sequencer. So on the fan relay and on the heat sequencer, designate for me the high voltage and low voltage connections. Where do we find the low voltage? With the single ones on the sequencer, it's on the bottom. The bottom connections on our relays. So,
Tops are always.
high voltage. Because we're either high voltage, the relays have 2 hands, so the heat sequencer has these 2 hands for low voltage at the bottom, and then it's 2 hands for high voltage at the top. The fan relay also. When we see our typical fan relays, it's a small rectangle, and we'll see 2 connections at the bottom all by themselves, and then no less than 3 connections at the top. And this is how you'll always be able to designate. I mean, it's written in very small, but this is how you know these are your low voltage connections on the fan relay, and these are my high voltage. So we're going to go ahead and connect these to the low voltage common, because common always goes directly to the hand. Put it in my hand says the relays. And we're going to do exactly that. And then the heat sequencer would also need its common. So we will run common down. Now, 2 of the relays have been satisfied. We have put common low voltage in 1 low voltage hand of the heat sequencer and 1 low voltage hand of the fan relay. Let's draw this in. The lines came out gorgeous.
Oh.
It came out gorgeous, though.
Oh, vicious.
It's really good. So now we see we have 1 more relay that requires put the common in the hand. Which relay is that? Excuse me.
Heat. Sure.
That has its, excuse me, heat sequencer.
Yeah, okay, it's heat.
If we look, the heat sequencer has its common in its hand. If we look, we see the fan relay.
Oh, so
The fan relay in addition has the common in its hand. So what is the one relay? We agreed there's 3 relays in this entire system. What is the third relay waiting for 12 volts of common in its hand?
Or family,
Well, that has its fan
we
relay.
have the family,
What controls the outdoor machine? What's the relay out there? It's right here. It's inside of every condenser. Our compressor contactor. Our compressor contactor is inside of every condensing unit. Our compressor contactor is inside every condenser unit and every split system. The reason the beauty of the designation of the split system is because we know that regardless of the electric furnace, combustion furnace, heat pump, or straight cool, you will have a compressor contactor relay outside of the condensing unit. And this compressor contactor relay is how we control and turn on and off both the compressor and the outdoor fan motor at the same time. So this is your contactor. Our contactor is our condensing unit relay. Our contactor. So we have our contactor. And what is contactor here? This is in our theory. What is the contactor saying out to the transformer? It's a relay just like the heat sequencer, just like the fan relay. It's a relay, it's a relay, it's a relay. Put this it. Put the common.
in my hand.
Put the common in my hand. Excellent. It's they say it in almost a gangster threatening way to the transformer. It behooves them. It behooves the transformer that common is put in the hand of every single relay. So in theory, we have connected the low voltage common. Put the common in my hand, every single low voltage relay says to the transformer, and we have done so. So we have completed every connection for the secondary common side of the transformer. Now, let's get that drawn in, and then we are going to connect it in the machine, in the application. And we're going to see how finally this theory, how finally it connects and plays out. Because tonight is when you learn the anatomy and now the physiology, how it works together. It has taken us many lectures to get here, and I'm very happy to be doing this lecture tonight. So now, inside, find, please, the common low voltage side on that transformer. David, you tell me the common low voltage side on that transformer. You designate top, left, right, and remember the transformer is not picky. It will work with any combination.
We'll go top right.
What would you like to be top right? Right here.
Common.
Common. Very good. David has designated the top right to be the secondary common. We have common. That's 24 volt common. We have 24 volt common here. In our theory, we've taken 24 volt common and we've taken it to every single relay. How many relays are here inside of this electric furnace? Two. And where are they? Physically, where are they? In this, remember, this is pretty much the scale. This is pretty much the scale, the application of this horizontal electric furnace. Under the transformer, what do we see? We see the fan relay here. Now we're looking at it. We're really looking at it. We see the fan relay. We removed every wire. We walked in. We removed every one. Not because it's necessary to fix it. It's because you are tired of looking at this and saying, I know this in my head. Why can't I see it in here? Now, let's do this. Let's get secondary common into the hand, low voltage hand of each sequencer. I'm here with my wires, my friend. I can add them here. Where would you like them? Tell me top, left, bottom, right of your fan relay. On the bottom, come here, selected the bottom because it only has 2 legs as opposed to the top that has no less than 3 legs. Komi now knows this is the low voltage portion of this relay, of this fan relay, the most typical relay I find. Now, of this, would you like the left or the right to be 12 volt common? Because the relay doesn't matter. It's fine either way. What would you like?
Doesn't matter.
No. The right? Excellent. Komi has select, Komi is designated. Do you see that? Do you see what I mean? What we have to get to when I say you're in control, you choose. You choose exactly where everything goes. This unit doesn't tell you, you dictate where the power goes. Komi is the designated bottom right 12 volt common. And I'll go ahead and add a wire. I'm just doing that big wire net here. How about that? So we can add what we need, yeah? Very good, all right. We're gonna bring this down. Very good, very good. Now, what other relay is inside of this actual application waiting for its 12 volt common in its hand? The heat sequencer, very excellent. And Komi, do you see the heat sequencer up in this application? Where do you see the heat sequencer? To the left, to the right?
To the left.
To the absolute left. Very good, Komi. Do you also see the connections? Do you see the connections for the heating element? Where do you see those?
On the right, bottom, right.
Right here, the heating element? The bottom left?
Yeah.
Excellent. Well, that's ours over there for the theory. Let us notice in real application how everything is centralized here. Very good, very good. Now, this sequencer, would it also dictate, mandate, and say to the transformer, you have your primary, put the common in my hand. Is that heat sequencer screaming the same thing? Okay, so tell me what to do, my friend. And I shall wire where you like. I'm connected here. Where would you like it, sir? Oh, no. Where would you like this common to go? You don't have to tell me, just tell me where you want it. Here. I can go any way I want. Where would you like that common?
You said the bottom portion was the low voltage, right?
I did, however, actual application, it's sideways on the heat kit. Because, and then look, see how we have it staged almost like a little castle? It's made like this, just so when you see it in the field, just so when you see it, it's very hard to mistake this. And that's how it is.
So bottom right.
Bottom right would be good. I'd like it. You're good. Yeah, very good. Excellent. Because you can denote the smaller. It's much smaller on the top. Our heat kits are designed, or excuse me, our heat sequencers are designed so we can see, even from far away, that the second stage on top, or the stage on top is a lot narrower than the bottom one. So that's how Komi knows that the bottom is the actual bottom in the correct secondary side. So the bottom right, he has designated to be common low voltage. So I'll go ahead and string us another one. Very good. Oh, now we're going this way. Right on. Do you see how now in the real application we're not so rigid with lines?
Yeah.
Because these are actual wires. And wires aren't rigid. They'll move and they'll flex at the very last second. So we have 2. Very good. Very, very good. Now, what is our final relay that is streaming? Put the common in my hand. The compressor contactor. Now, the compressor contactor is not in this indoor machine. No, it isn't. No, correct, it is absolutely. Is there anything that's inside of this indoor machine that I know terminates outside of the condensing unit? That every split system has, regardless. That I can anticipate there's always going to be 1 entering and 2 exiting.
The thermostat wire.
The thermostat wiring. It's been there the whole time. In fact, when you took panels off, you started seeing things you couldn't see till you took the panel off. So now that when you take the panel off, this is what you're seeing. You're seeing something similar to this. You took off your panel, now you can peek inside the machine. And now when you do peek inside the machine, this is what you're seeing. You're seeing almost like a blue. When you peeked it in, that was going this way and disappearing off somewhere. You saw what looked kind of like a yellow, kind of running with this one too and disappearing off somewhere. And then you looked at your other thermostat control wire. And then you looked at it and you saw a blue that trailed off somewhere. And then you saw a red also that trailed off with it. And then you also, with that bundle, with that thermostat bundle, you also saw a green being occupied, which struck you as weird because when you looked at the other bundle, you could see the green was wrapped around it, like it wasn't being used. Odd. And then you saw a white trailing off and purple instead of white now, but you saw another low voltage. So one has two, and then you see a yellow. You see also the yellow coming off and disappearing somewhere. So now looking at this, and we discussed last lecture, how many low voltage wires does a heat pump have? How many low voltage wires does a straight cool have? As one of the ways to tell them apart. Do you remember how many our straight cool had? One had 5 and one had 2. So how many low voltage wires would our heat pump have? With needing more control, it would have the 5. And with the straight cool having less control, how many thermostat wires would I need outside? Correct. Now, I will tell you this, the thermostat bundle always needs at least 4 wires. So now when I'm standing here, and I'm looking at this air handler, I'm looking at the electric furnace, the air handler, I've taken it off, and once I've taken it off, I see my 2 thermostat bundles. And when I remove it, now I can see wires that are kind of just going around hiding, but I can see one clearly has 4 and 5, and one has 2. So what do we know? Which is which? We have one on the left and then one on the right.
The one on the right is for the thermostat.
Very good. The one on the right is for the thermostat. The one on the right for the is for the T-stat. And one way you can tell is if you look, is the green being used by that thermostat bundle?
Yes.
Yes. Is green being used by the other bundle? No. So this is the condenser. Because what is the relay that requires green? Low voltage for secondary green. What relay is the one that requires green from the thermostat? Well, that's yellow. And white is our sequencer. So what color would be left? What relay would be left? If we need to turn on the fan motor, we're going to need this fan relay to engage. And the fan relays are green. That is our green wire. So when we see our green wire, and we don't know where it goes, we just see it's occupied. And then we look at the other bundle, and we see that green has been wrapped around, it's not being used at all. So just knowing that this one is 2 and doesn't have the green used, and this one does, can help us isolate which one we're holding.
Absolutely.
Yes, 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 excellent, excellent, excellent. Now, back to business at hand. We got a compressor contactor saying, put the comment in my hand. I am your wireman. I got your blue. I've gone to the wire cap. Where do you want it, boss? Left or right?
Right.
Well, right has the green, so the right's going to the thermostat. Where am I trying to go?
Sorry, I thought you meant like go to the left. Yeah.
We're going to the left. Might as well just throw a little wire cap on there. Why not? Yeah? Very good, baby blue. Very good. So now I have a wire cap at the blue wire, at this thermostat wire. And then where's the other end of this thermostat? Where's the other end of this blue that I just wired into the blue? Where is it? Where can I find the other end of this thermostat bundle? It's got the green wrapped around.
The compressor contactor.
Yes, sir. Compressor at the condenser. Excellent. So what do we have to do? We have a compressor contactor that is waiting for comment in its hand. So let's do that. Now we're out here. We stepped out to the condenser. We found the thermostat that goes with the line set. We're in the condenser. Now, what is this compressor contactor screaming through this wire that it wants from over there?
You use that common.
He wants that common, yes, sir. So now you've taken this thermostat bundle that you found that you know you connected inside the indoor machine. You know you buried that blue wire down. You know you put it in a wire nut. And here we are outside. So let's take that blue and finish the mission. Let's get blue out and put the common in my hand. Does this compressor contactor, does it have common in my hand?
Yes.
Does it have it via a 24-volt thermostat wire that we can anticipate will be on every single type of split system that we're going to interact with?
Yes.
Excellent, excellent. Are we done with secondary voltage control? May I put the blue down for now? Very good. Transformers, the neck, we still have one that's not connected. Where are we going with it? Where is our 12-volt or low voltage control? Where are we heading with it? Where did we go with it? Let's go on our theory first course. Where do we take low voltage control? Well, the fan, if I took it to the fan relay, then the fan relay would be stuck on. I need something that can hold that 12-volt control and shuffle it out as needed when I need to control these relays. So where do I take this 24-volt control that's opposite the common?
To the thermostat?
Yes! What color on the thermostat will land? Doesn't matter the wire. I didn't ask that. I asked, what terminal on the thermostat would you like me to land? The wire that's leading here.
The C?
That's if I'm this one. I'm control, red. So where am I landing?
On the red.
On the red, correct. C is optional. C is optional. So we're going to take control and we're going to go make a jump here and land at the red of the thermostat. Now, when I say 24 volts, I like to think that we have 12 volts common and 12 volts control. 12 volts common, 12 volts control. Do I have 12 volts common stationed at every single relay in one hand of the low voltage? Yes, I do. Yes, excellent. Now, I need to get 12 volt control to the other hand of every relay. Once any of these relays receives this 12 volt common in the other hand, then the relay will open its pathway. It will do what it's designed to do, but not until we get control secondary voltage to it. I like to call it its 12 voltage or 12 volt control. Now, we have run to the thermostat. Okay. Now we're in the real life. This connection down here in real life is where on this transformer? Left, right, top, bottom. Put me in the right place.
It's going to be right bottom.
Right bottom, excellent. That is this. That is secondary control. Very good. I will get a fresh wire strip. And would this be a connection being that it's on the secondary side? Secondary side, would I ever want to connect anything that was primary voltage? Or is this going to some sort of low voltage wire? A low voltage wire. A low voltage wire because it's secondary low voltage. So when we take this up, I need to get that to the thermostat. Do one of these bundles end at the thermostat?
Yes.
Every single time. Which bundle? Would it be my left one that has the green wire not being used? Or would it be the right bundle that is having the green wire being used?
The right bottom.
Because, and how can you tell that's the thermostat? How can you be sure?
Because the green wire is being used.
Because the green wire is being used. Excellent. So off we go. We're going to start here. And we're going to take it this way. And off to the red I go. And then I'm going to make this a wire cap here. Excellent, of course. Because what we have to have in common is, again, when these low voltage wires come in, they don't just get connected magically. There will be a wire nut. There will be a low voltage wire nut for every low voltage connection. So we will draw it in because you understand that's how we have access. That's how we can change it. Because we have a wire nut, a little blue one. Every single one. So now we can connect and we can take this voltage outside or wherever we need. So let's take this and know that this other thermostatic control wire here, the other end of it is where I need to take this, because this control goes where? To the thermostat red. Very good. So now we are here. So how do I replicate what I've done in theory in real life application? So bear this wire down, find, well, what color did I connect there? So what color do I know to connect here? Red of the bundle. I pulled red out of the bundle, correct? Brilliant. So the red in the bundle has what I'm seeking. Very good. So we're going to take this red and we're going to land here at the red of the thermostat. Now, let me ask you a question. Is 12-volt control just waiting there, just sitting at red? Is that what I have going on here?
Yes.
12-volt control red, because it's coming and it's controlled till we put the red in. But now we understand with every split system, the red that's in the thermostat, when we're at that thermostat and you see that red line, where are you going to find it when you get to your indoor machine, regardless of what it is? You get to that indoor machine and you find that red, and you understand this is going where? To the control, to the secondary control, and it all starts with, what did I say was the neck? What did you call my man? The transformer. That is our key to getting this wire. Let's keep going now. Now, we've got 12-volt control on the red on the thermostat. We've got it done in real application, and it's done in theory. So now, in theory, if I needed green to turn on, what color wire leaves the thermostat and arrives at the fan relay? Or what color does the fan relay typically use to get its control low voltage? Green, correct, correct. So let's do that. Let's take green down from the thermostat. Let's run it over. We have to jump over the wire, have to bridge. Come up, and then up we are. We have now connected green, control green, through the thermostat to the fan relay. Because every single thermostat has a fan on, fan auto option, where you can turn on only the fan relay. And that's how it does it, because the 12 volts come and they sit, and 12 volts enters. 12 volt enters on the red, and then it is held by the red until the thermostat says, the humans want motion of air. And then they set it to on, and the thermostat opens the channels and then sends its control version down the blue, or excuse me, down the green, because that is where it's going to find the fan relay. So voltage, 12-volt control voltage enters on the red and exits on the other colors to the relays. See, it's the thermostat that takes control of this voltage and gives it out as the humans tell the thermostat to set it. So now it arrives, green has been set to fan on, voltage finally arrives. And now this fan relay has its 12 volts of control, and it also has its 12 volts of common. It's had its 12 volts of common. It never didn't have its 12 volts of common, because as we said, a common is a steady, solid, unbroken line. Here they are. So now we've connected green to the other low voltage side of the fan relay. How do we do it in real life? I am ready for you. Where would you like me to connect your green wire I just paired, or I just made?
Bottom left,
Of the,
fan relay.
and you designated the fan relay bottom left, because you understand this is only 2 connections, not the minimum 3 that the high voltage has. Very good. And we have a fan here, so let's get our wire cap ready, no?
Oh, yeah.
Yes. And let me clean this green up, it's a little bit there. Oh, that's ugly. These are little clean. Hold on, here we go. So I have a green wire. Get my little wire nut action, it's there. And then I'm gonna grab another green, and here we are. Here's our fan relay. Which one? Well, we already designated the common, so I'll be opposite. Here we are. Just like in theory. And then we're gonna take this up. And we're gonna go. And it's gonna, remember, it can lay on this and that, it's fine. Here we are. And then we're gonna put a wire nut, because that's how we made the connection. Right on, right on. Right on, right on. Now what's left? We've taken our green. What is next? Our white or our yellow?
Yellow.
Let's go with yellow, right? Now, for yellow will not show up very well at all. So what I have is kind of like a fire orange. See this? Now this is very important because when you recreate this, when you create this, when I tell you, students, that you will be to the point you need to be where you can write this on an application, on an extra sheet of paper and turn it on and display that you have high voltage, low voltage knowledge. And when you do that, in a case where you can't use a color, then you have to make a legend. You have to make a legend. You write on your paper, legend. And then when you write legend, we are saying this is now yellow. So draw it in, grab your orange and draw in a legend. And you draw a little square of the color you're representing. And then you draw it out and you put secondary yellow. Secondary yellow. Now, when I say secondary yellow, what does that imply? What does the term secondary? I don't say secondary much. I haven't really said secondary on any lecture we've done. So now that we're talking about a certain type of system, when I say secondary, where am I talking? Low voltage, yes. The word secondary implies low voltage. Call me, where do I find the low voltage? On the primary or secondary side? Secondary. Now, I say secondary yellow. Secondary, because I'm on the 24-volt side of the transformer. Beyond here, within the secondary, there is a yellow that is typically used. And it is the yellow from the thermostat to control the compressor contactor. I have written, when you think secondary yellow, oh, secondary side, low voltage yellow, oh, the yellow we use here at the thermostat. Just the designation gives it power of communication and clarity, and that you understand and can convey that you understand this, that you understand the theory, the principles. Because regardless if you go HVAC, regardless if you go any type of refrigeration, yes, as we go, refrigeration does change. These things change, but one thing they almost have in common is low voltage control. Low voltage control is crucial for any type of HVAC/R. You will have transformers and relays. And I say low voltage problems are the Achilles of so many technicians. So imagine when you land and you've been saying, put me on service, I'm on service, I can troubleshoot. And you get out there and you're finding low voltage problems. Very, 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 very important that low voltage is something that we can see in theory, because it takes knowing these rules and theories to apply it. Now, let's do this in application that you've drawn it in. I need to get yellow from this thermostat physically. I need a physical pathway all the way to my real in-line compressor contactor relay. What would I use to assist me for this pathway? So when yellow sends a signal, or excuse me, when thermostat sends a signal down yellow, that I can actually connect. Forgive me, guys. And we have green connected, forgive me, there's green. When we do two, it's fun. And we also had our heat sequencer as, oh, not yet, very good. Yellow. What color has our legend told us we are using? Kind of a hot one?
Yeah,
Hot, kind of fluorescent. So, here we go. Where would you like this? In the yellow? Very good. We buried it down. Notice no wire caps here. Notice wire caps in every indoor machine of any split system. Yellow in place. I'm here, and here is this yellow. What do I know about this yellow? Is it receiving? This is set to cool right now. Now that it's set to cool, is voltage flowing? Is that 12-volt control flowing from the red into the green and the yellow as well? Yes, it is. So I need to get the voltage that's here. And I know this one's here because look, the green's connected. So I know there's a fan relay involved, not a condensing unit with this bundle. And now that I have it, now that I isolate and know the voltage is here, where do I need to take it? Where does it have to go? To lay where it wants to. Yes. Excellent. It needs to go to the condenser.
Would you run it for the other set of wires?
Excellent, 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 excellent. In air conditioning under 5 tons, there will always be this, unless we get the higher SEER systems, but for the majority of everything that's installed, 14 SEER, even 15, you are gonna have a yellow that I can add for you. We're gonna take it over here, I'll add some here, drag it over, bend it over, and oh my, oh my, oh my. Here we are. Have you successfully made a clear pathway using 2 thermostatic control wires that you now know will be on every split system you encounter, and taking this yellow from the thermostat bundle to the condensing bundle, therefore sending that control contactor voltage down the line set, and finally emerging at the other end of the thermostatic control bundle. I am here, where would you like to put me?
Right side?
Opposite the what? Opposite the common. Brilliant! We have control now in physical contact of the compressor contactor. But what did it take? It took the recognition that every split system, regardless of heat pump, straight pool, combustion, or electric furnace, is going to have its 2 low voltage thermostatic control wires. And when I tell you we have the panels on, that's why I say you have to be able to isolate these wires. Before you even think to worry what's inside of this, you look at the exterior, because now we know every indoor machine is down to a combustion furnace or an electric furnace. If I have a combustion or electric furnace, will I always have 1 high voltage in and 2 thermostat bundles out? Yes. If I have an electric, will it be the same? Yes, the same. Will I have a heat pump? Will I still have 2? Yes. If I have a straight pool, any combination will always have 2 thermostatic bundles. 1 down the line set. We learned the line set must be shared by every split system, regardless of combustion, electric, heat pump, or straight cool. Very, very excellent. What do we have left? What is next? What is our next? Let's do it in theory first. What is next? What do we have leaving the thermostat in theory? Where do we need to go with it?
White.
White. On a whiteboard, what did we learn that we do in a case like this?
Go to the legend.
We create it in the legend, and we put it in, and we select the color. We're gonna go with purple. Again, here we are, purple on the legend. We draw it, and we put the purple in there. And again, secondary, white. When I say secondary, what is that designation alone implying? Where am I in the system?
Transformer on the low voltage side.
Yes, sir. Just with the word secondary, we have designated where I am. At the transformer side, secondary, receiving low voltage. And when I know I'm on the low voltage side, and I have a white, the only white that we use in the low voltage side is the white that feeds the heat sequencer. So in theory, we're going to drop down and now send a voltage out of the red, out of the thermostat, from the red where it goes in, out of the white, and make our way to the heat sequencer. And we're going to land opposite where? Where do we land opposite our white on that heat sequencer, as well as every relay?
Common
Absolutely common, because we know what? Before we connected any wire, which one did we connect? Which one? Common in the hand. Every relay says to the transformer, put my common line, and gentlemen, look, it's a still line, unbroken. No breaks in the common. We have broken the red control by the thermostat. And that is the same application. These are what we learned that make replacing every wire. Because I said, you're the ones that designate where voltage goes. Let's finish this. We have purple secondary white. Here we are. Where are we taking this?
So we'd be taking it from the top right of the heat sequencer.
And how do you designate the top right 12 voltage control? Because you recognize the very shape of the heat sequencer. Because now in this actual application, now it's sideways. Because this is how every heat kit is installed into every electrical furnace. 5 kW, 7 kW, 10 kW, they all install at the electrical portion. So yes, here is our heat sequencer. And here is our white wire. And here is our bundle that goes to the actual thermostat. And again, in real life, this wire is just laying. Here we are, connected. In theory, we have to jump. In reality, this is what we see. Now, one more low voltage cap. And now what are we connected over there? White? That's all we have left. Now, let me ask you, gentlemen. Let me ask you, have you replaced every low voltage wire? In theory and in the application. Everyone. When we got in here, I told you would be able to. And I told you, half of you will be done with this before even I'm halfway done. Do we see now the connection of theory and application? But it doesn't happen until you recognize, regardless of the split system we have, which is 97% of the units in Florida is split systems. Because if we're not a split system, we're a package unit. And all of our refrigerant components are inside a package unit, attached to a place that doesn't have much space. When we're a split system, we have half of the refrigerant cycle in an indoor machine, half the refrigerant cycle in a high pressure condenser. When we're the indoor machine, we're defined into a combustion furnace or an electric furnace. If we're the condenser, we're going to be a heat pump or straight cool. Now, regardless of all of those, the thermostat wires remain the same. And the line set that carries the suction line, liquid line, low voltage thermostatic control stays the same. That's why I say, gentlemen, before you look inside, look on the exterior. You've lost voltage inside. You don't even know where it's at. Look outside the machine. Look out and find where it enters the machine, because once it enters the machine, you grab it and then you dominate it. You tell it, you give it its designations. You control this voltage. Not the other way around. Let's finish this. Now the high voltage. We see the concept of put the common in my hand. Inside of this indoor electric furnace, how many loads do I have? What two loads could potentially produce work on an amp drum when providing voltage? Heat kit and fan motor, that is 2. With the same, put the common in my hand. We learned in the case, 2 hands of low voltage. Put the common in my hand. Put the common in my hand. We also said that the relays have 2 legs of high, 2 hands of high voltage. And they also say, put the common in my hand. Who are they talking to now? Do they want low voltage common? These are high voltage L1, L2 loads. They want high voltage. And they scream to L1, put the L1 common in my hand. Put the L1 common. Gentlemen, regardless of how many relays you have, every relay low voltage will scream, put the common low voltage in my hand. Regardless of how many loads you have, how many motors, how many heaters, every single one will have 2 connections. High voltage. Put the high voltage common in my hand. The same exact application. Working for the high voltage now. Do you see, gentlemen, it's how these rules that we can rip every wire out. That you're not just replacing parts and hoping. You have your meter to also go along and do readings and confirm as you're going. Let's do this. Now, indoor fan motor 5 kW. I need someone to designate L1 common. We have 2 connections in each. David, designate L1 common on both, please. It does not matter which one you choose.
Top,
Top, indoor fan motor,
oh, yes, the indoor family.
very good, and for our 5 kW heat strip, please designate.
I will go ahead and go with the left side.
Very good, the left side David is chosen. These are now L1 common. And just as the low voltage, put the common in my hand, it goes uninterrupted. This is valuable when we troubleshoot, because if we can already know that certain wires will not be a problem because they do not, or they are never broken, they go directly to where they have to without a break, then they can be eliminated as possible sources of the problem. What's more likely to fail, a physical wire or a component that's designed to fail? But knowing where to find each component is what this is about. Now, what have you done? Indoor fan motor, you just got it. You just got, exactly. Indoor fan motor, let's do it inside. Find my indoor fan motor, find my L1. Oh, look, it looks to be buried by wires. We'll see that too, but what do we see? Find the fan motor. Here we are. Do you see L1 and L2? Which one would you like designated?
L1.
Here we go. Looks like it's behind here on the green. That's okay. I've made my connection. Where is my L1 and L2 entering and landing? On every electric furnace. The heat kit itself has where you land. So where do I need to go? Where did I put my L1 on my transformer? My transformer primary had its L1 also. So we need to bring it towards the high voltage. And we'll go right in the same terminal, because there's 3 that we fed L1. And now it's a thicker connection, but way less wire than theory. Look in theory, the madness of how much inking wires we use. Look in application. This is to scale. Look at how much more sense it makes now. It makes more sense in application than it does in theory. And that's the beauty of once you have theory down. Now let's keep going. We have L1. What about our fan motor? What other L1, L2 load that is capable of producing a 52 to 54 amp draw is going to be sitting that wants that L1 common? The heat kit, very good. It's right here, the heat strip. Boy, that's a short trip, ain't it? Again, practical application. This inside of our theory looks like this. It's pretty wild. That is a lot. But again, it shows that you understand and respect the designations and the rules. That will never change regardless of the type of system. This is high voltage. This is low voltage. Now again, we've done that right here with a 3-inch wire, 5-inch wire. It makes more sense when you can take theory to application. Now let's keep going. What about L2 on these high voltage components? These high voltage components require L1 and L2, and they require that to run. Will they run if I only have one line of voltage to them? No, they will not. They will not operate. They cannot spin. They cannot break the inertia of sitting still without both lines of voltage. So that is why, put the low voltage common in my hand, loads, put the high voltage common in my hand. I want my L1. Do not play with my L1, because I can always be in a state where I have one leg of energy and not energize, not produce work, not produce an amp draw. So what do we do with L2 now?
Connect both sides, or every other side.
We connect our L2. Let's bring it over. In theory first, gentlemen. Which one do I start with? I am your wireman. I'll put it where you want. Indoor fan motor, shall we?
Yeah, the indoor family.
Very good. And see, we need to get here to our L2. Let me see if I can take us. There we go. Here we go.
Well, that's the heat kick, isn't it?
Oh, what did you want this?
I wanted that one on the indoor family, please.
Correct. Very good. Indoor fan motor. We are going to go to L2. Very good. We're going to bring it up. Very good. Bring it over. And we're coming down to L2, because this is what that load requires to activate and begin to perform work. So right now, if we were to turn this on, is this indoor fan motor performing work? Is L1 and L2 present?
Yes.
Excellent. Now, what load, let's go ahead and, what load do we have left inside, in theory, what load do we have left? Very good, the heat strip, excellent. And what is it seeking now? It has its L1. What does it want to be able to perform work? Very good. Excellent. So let's do that. Let's get L2 to the other side of our 5 kW heat strip. And let's bring it back. Ooh. It's getting hectic over here. We can make it though. We can jump over this, jump the bridge, up, over. Again, the half moon bridge to show, to indicate to the people that are reading your wiring diagram that you can show when a wire is crossing over another. Because you're not always going to have colors or colored pencils. That is today just to learn the theory even better. All right. We have L1 and L2 at every L1 and L2 load inside of the electric furnace, L2 and L2. Are both of these loads energized right now?
Yes.
They're both energized. So they're both performing work?
For the heat kick and the indoor fan, yes, they both have the L1.
So the house is nice and warm. It is, very good. But now how do we turn them off? How do we turn them off now? How do we turn these off? We know L1 common is never broken. This is what the transformers and relay are about. Low voltage control. This is everything, gentlemen. This is what we've done. When I say a relay is a relay is a relay, I mean that the job of a relay is to receive secondary low voltage on both of its hands and then close a pathway. For instance, when a fan relay closes, it will open a pathway from a high voltage connection to the other. When the heat sequencer is engaged and receives its voltage, a bimetal will float up and then connect this pathway. When the electromagnetic coil, magnetic coil that's underneath this contactor receives its 24 voltage, it will sink down and then bridge the gap, allowing voltage to flow. So when I need to control a load, this is the point of the relays. Because now, instead of running directly to this heat kit with L2, what we do is we wait till it almost gets right here. And then we say, whoa, 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 bring that L2 control here. You're not ready for that. You're not ready. The thermostat doesn't want it. The humans don't want you on. No. But I'll let you know when the thermostat says you can go and activate. Every heat kit, every load will have a relay because it's how we have thermostatic control. Every single one. Fan relay as well. We can't just land L2 here. We won't turn off, but we can take it and we can divert it. And we divert it, we take it to the fan relay, we land it on one leg. Doesn't matter. The relay really doesn't care. It will open a path in either way. The relay doesn't care in which low voltage hand you put it. It just wants it in one hand. That's the beauty of a relay is a relay is a relay. Because they're all the same. 2 hands of low voltage, 2 hands of high. So look at what we've done here. Now we bring it back. Now, once we open, we'll have our 12-volt control coming back, jump over our wires, and then we'll bring it back to the L2. And we are there. So now, when that fan relay closes, because it's received the 12-volt control from the thermostat, it will close. The relay will energize because it's received its voltage. And then it'll close its circuits and pathways to turn on. Gentlemen, this is how we control high voltage with low voltage. Not just low voltage. Think about it, gentlemen. It was 12 volts common in the hand of every relay. I didn't have to bring 24 volts to the fan relay. I didn't have to bring 24 volts to the heat sequencer. I didn't have to bring 24 volts to the compressor contactor. Why? Because what was in the hand? Common. And common has its consistent 12 volts. And the same thing applies with our L1, L2 loads. Does this not seem so insane anymore? The same principles, gentlemen. Now let's go, let's finish this. Here we go. L2, we'll start with our fan motor. Where do I want to take this L2? Am I going directly to L2? Will it turn off? What do I need to brake? What do I need to stop?
You need to put it to the fan relay.
Yes, what side? Designate, please.
We're gonna go, just for the sake of that one, let's do the top right.
Brilliant. We're taking L2. Well, that's a short wire. Bam. Look at how long that wire is. Do we see how theory is wild? We look at theory, and yes, you get the theory, but that does not look like an air conditioning system. This is the application, and this one does. Exactly, very good. Excellent, excellent, excellent. So let us do the same. You guys are drawing it in, very good. Let's go ahead now. We're taking this and we have to get back to L2 coming in.
Go to L2.
That's right.
Center.
One of our connections there. Is this where you want?
Do the center one.
I'll do that. Bam. Very excellent. Now, what load in this air handler still needs its L2?
The heat sequence.
Yes, it does. The load.
All right, I guess that goes to
So which load? What is this? A 5 kW.
the heating element.
Yes, sir. Brilliant, brilliant word. Yes, our heating element requires this L2. But do we run it straight down? Because what would we do? We'd be dodging the relay. We'd be dodging thermostatic control. This is all about the power in the thermostat. So to the relay, you say, I can do that. There you go. Connection. What's next? Where would you like opposite where I just parked? L2. Where should I put this? Right here? And then where would you like the next wire?
Right over there, it's that heating element.
Wow, like 7 inches away? So I only need a 7-inch wire in real life, not 4 feet?
Beautiful thing.
Didn't I tell you you'd be very excited before the end of this lecture?
I do have one question when it's all done.
My man, we're getting there. So here we see, gentlemen. This is it. Comey, how do you feel, brother? Because I told you guys would have this wire today. I told you, my friend, and you've drawn it out piece by piece. How do you feel about this, my friend? Are you good?
Yeah, the only questions I had about it were the relays, but you explained it well, so I'm now, I got it.
Brilliant. Brilliant. Let me get a time check.
10:15.
Is it really? Okay. Brilliant. Gentlemen, let's cover. This is brilliant. Now, we understand that this is going to be the same application. Voltage will be different for our combustion furnace because what will we not find in the combustion furnace?
L2.
L2, correct. So if we're not mandated by L2, if we don't have the necessity for L2, then what does that implicate? What does that imply when we don't have to have L2? That we don't have a heating kit. Correct. And if we don't have a heating kit, are we mandated to have L1 and L2? So what can we roll with in a combustion furnace? Hot neutral. Oh, that what a beautiful designation. Oh my, very good. Excellent work, my friend. Gentlemen, do we have any questions about this?
Yes.
Okay, let's do this. Let's go ahead and definitely do a question live because somebody else may have it. And this, gentlemen, is our final lecture of the mod. And I will be holding class every day next week.
Yeah,
No more time, yes.
I was.
Despite, the campus is open, so despite everyone, yeah. So anyhow, let's get down to, what was your question, my friend? Let's do it. What do you got?
So, I'm pretty sure you covered it at some point, but on this, we still have our C is open, our common.
It is.
And what
It
are we
is.
doing with that?
Very good question. Tell me, what do you think? Did you have that question about the C on the thermostat that's open, and the C that's open in theory?
I remember last time we were in here, you said you wanted to connect commons when, so we don't have batteries. So you can
Correct.
always, you can always change it, right? You can always,
Well, let's look at it like this.
I mean, not change, but you can always add.
When you look at a thermostat and it says optional with batteries, that's what it means. That means that this majority of Honeywell's thermostats will say, when you're replacing the thermostat, it'll say C is optional with batteries, meaning that I can either send this red down the corresponding low voltage line to the relays without C, but I need 2 batteries to stay lit.
Right.
Or if you provide me common, just like you provided the relays, then I will no longer need batteries.
Gotcha, okay,
That is the point. That's what they mean by C is optional with batteries.
gotcha.
Now, when we have C optional with batteries, what happens is the thermostat changes function when we actually do not have batteries. Because what happens is, if we do not have batteries and we are drawing power from C, then it looks like this. We're taking one more common wire, jumping it, and bringing it down and terminating at C, okay? So let's do this also in application. Okay, here we are. Here we are, here we are. Very good. Now, we have C. You guys see it right there. We clean it up, we bring it down, and you'd like for me to put it to this big C wire nut I have here, correct? Okay, let's do that. I can do that for you. I'm the wire guy, I got all the connections. Okay, we just wired C that terminates over there into thermostat. I'm gonna add a wire, and it's gonna run down to my common bundle that has a much bigger wire nut because it's supplying now 4 wires are now coming off. Put the common in my hand, 4 of them. Now we have 4 wires, so that's okay. That's what different wire thermostat, that's what different ones says wire nuts are about. But now we go here, and we take our blue. Let's say in that application, the blue is wrapped around. So you've added blue on that side. When I keep saying that it's you that designate voltage, you dictate where you want voltage. But you have to recognize that with every split, there is the thermostat wires. So when you're at the thermostat, you understand that now these wires will end inside of the split system regardless of its climate. And then we take blue and we unwrap it. And we land it right here at C. Do I need batteries in this thermostat anymore?
No.
Now, how many volts? We had red. Red was the only one bringing voltage in at 12 volts control, and then it would exit the wires to go to the relays. Now, how much volts do I have at the thermostat that I brought control voltage?
24.
24. Why would I like that? Why does that make us happy?
Up to,
Because now, when we troubleshoot, we talked about troubleshooting paths. We talked about walking in. We talked about when you ask the homeowner, the first question you ask, hey, I'm John. Is the medic here to take a look? AC's not working? They tell you. And then right then, you don't let them take you somewhere. You don't let them say, hey, I think it's this, come here. I think it's that, it's this. No, you start your own, you ask them one question. Okay, yeah, sure. Sir, let me ask you, when you put your hand up to the vent, are you getting air or no air at all? And when they say, oh yeah, there's air, but it's just hot air. Now through looking through your meter, you know that you have L1 and L2 because the fan motor is running. Your transformer has primary and secondary because the fan relay is closed, allowing the fan motor to run. So when you do that, you know where you have it and where you don't. What was your question?
and this, and what we're doing at this point, since we have the common connected to the 24 volts.
Yes.
From the thermostat.
Correct.
Would it be safe to say that even if the fan wasn't running, you would be able to almost troubleshoot to see that if the thermostat didn't have batteries, you're still drawing power from the transformer?
Brilliantly said. So that was the question. Can we use it? And I said, now we turn the thermostat into a diagnostic tool because when we do have the common connected, now we have 24 volts that is originating where, if it's right, at the indoor machine that's up in the attic. So you just walked in on your first call with nothing but your 10 and 1 and your meter. And before you even gone up there, grab the ladder, okay, no air at all, you know I have to start at the unit. You go first to the thermostat, you pull it, and you find they do have a control. They do have red, meaning if high voltage is good, low voltage is good, transformer is good, no float switches are engaged, I will be able to pull a 24-volt VAC reading. And when I pull that, now I know L1 and L2 have 240, primary has 240, secondary has 24, and I haven't even gone back to the truck to get the tools yet. You've been in the house 47 seconds. This is what brings the troubleshooting path down. The questions of where do you have voltage, where don't you? And now with common, now that we have common, powering our thermostat, what happens now is, now thermostat is dependent on it. So what will happen is if you lose power, your thermostat screen will go black. And when it goes black, that itself is a diagnostic help because it'll tell you what's going on. Meaning, this is a thermostat in your home. Okay, it's got its common, you just put the lid on. You just put your cover on, and then you have a screen. You have a screen right here. Very good. And then you have your buttons. You have BAM. BAM will always be on or auto. And then we have system. And that'll be off, cool, or heat. Now the thermostat is lit. It says 74 in cool mode. But what happens when we lose low voltage or high voltage? Now the thermostat doesn't have batteries. When it had batteries before, if we lost any kind of voltage, the thermostat would stay lit because it has batteries. And now we have thermostat, we have no batteries. So now when we've lost high voltage or low voltage, the thermostat goes blank. And when it goes blank, we just confirmed a problem. So now when the homeowner calls and says, hey, my unit's not working, now they can say, hey, my thermostat's blank. And that right there just tells the technician on the way, okay, blank thermostat. Right now you have high voltage, low voltage out. One of them is not working. And then you look at how old is the machine? This machine's only 3 years, 2.5 years old. Your guys installed it. It shouldn't be doing this. I'm in the heat. Well, what's wrong with it? We take our control voltage right here. Before we run it to the red, we do break a few things in with it. We will break our control red and put a float switch. We have to realize that every indoor machine will have a drain line. And this is a drain line that leaves the indoor machine, the evaporator, and drains outside. So this is a drain line, and then we have a float system. A float system is a little cap that has 2 wires and a float inside. And this float sits in the physical drainage tube, the main drain. So what happens is, if this drainage becomes blocked, this float will rise, because if the drain is clear, you're only supposed to have a little bit of water streaming on the bottom. Only ever should you have a little bit of water streaming. But if you're in a clogged state, the whole entire pipe will be full of water. And now the float switch rises up, and then it cuts the circuit. So what we do is we take our 12 voltage control right here, and before we send it, there is a float switch that's sitting right here on the drain pan, and it goes off with the drain line, and these are the 2 wires. So we run these 2 wires in the machine, and then we cut it anywhere we want. We bring it into the machine, and then we cut 1 wire to the red, and then we cut the other wire to the other end of the red that originates. So now the voltage has to travel through the float switch to be able to head all the way to the red. Meaning voltage leaves, travels through the float switch, and then carries on to the transformer. Voltage leaves, and then it's diverted right here. It's diverted right here into the float switch. And then it's brought back to continue on into the red, to the thermostat, to give that power, to keep this lit. So now when we have a float out, that will kill the voltage and make the thermostat blank. So this customer is pretty hot, saying, hey, this is only 2 years old. How is this breaking? The thermostat's blank. Now you look at history. Unit's 2 years old, too early for electrical breakdown, too early for mechanical breakdown. but that drain line that stays original in the house stays. So now you know that's the problem, just a float switch. Because more than likely, it's the float switch that's gone up and interrupted the circuit. More so, what happens when you're on the way there, because you're running nights, and then the thermostat suddenly comes back on. And it comes back on, and it's probably like 88 in here because it's summer, it clicked back on. That's because enough water has drained out for the float to fall for a little bit. And then when that happens, it opens the circle, we turn on the thermostat, and it turns back on until the water fills back up. So guess what? That same homeowner calls back and says, hey, guess what? It turned back on, you don't have to come out here. And then that's when I giggle and I say, ma'am, I'll be halfway there in about 44 minutes when it turns back off again. Because they don't understand, it was a float switch. And that water will fill back up. And then it will have to be cleared or it will stay off again. So that is why we have Common at the thermostat, to turn it into that diagnostic tool. Because if we don't have that, whenever we lose anything, it's still gonna be lit. Now the homeowners don't know, they think it's lit, oh, it must be good. I don't know, but it's hot. Where it goes and it goes blank. Now they know for sure, now they make the call. They don't wait for it to come back on, they'll call you. And that's why we keep Common. But again, the connections all happen here. And guys, we have got to get that, that's our cue. Thank you guys so much in Zoom for watching the L1, L2 high voltage, low voltage video. You guys have a wonderful, wonderful evening.